So that works?
Yeah, this works.
Excellent. Okay, sorry a bit for the delay. And thanks to everybody for coming to this special seminar occasion today. And we are very delighted to have Dr. Abhijit Anand from IUCA giving this talk today at the School of Astrophysics. So Abhijit was an undergraduate student in the first, I think he was in the first or second? Second, yes. Second 4-year bachelor's batch from Indian Institute of Science. And we had many stars coming from the batch. One of them is Kishore Loide, whom some of you have not met, but he was a speaker here a few years back. And then Abhijit went to, so he was the IMPRS PhD program. He joined there and did his PhD from Max Planck, Berkeley. And then he was a postdoctoral fellow at UC Berkeley. And then after Berkeley, he came back to IUCA Pune as an independent postdoctoral fellow, but then he's also having this collaborative work with Max Planck Institute, Max Planck Berkeley, and there is this collaborative work between IUCA and MPA. And Abhijit has worked on diverse topics, and then, for example, he has been instrumental in working with the DAISY, developing the DAISY pipeline, and also a DAISY scientist. Today, he's going to talk about tracing the cosmic metal cycle. So effectively, observational probes of the circumgalactic medium and the IGM from redshift 0.4, pretty low to the very high redshift universe. How you look at the IGM and CGM. And we did not get a lot of chance to talk with Anand, to Abhijit today, but there are some people here at the School of Astrophysics who are actually working on some of the stuff that probably Abhijit will be talking. And so without further delay, let's welcome Dr. Anand and Abhijit, please.
Yeah. Thank you to Professor Suchetna and Professor Ritiban for giving me this opportunity, and I'm very happy to be here. This is first time I'm visiting Presidency. I have been visiting Kolkata for quite a few times, but I have not been to Presidency. So I'm very, very happy, and it's very nice to talk to all of you. Actually, very nice to know that you all are working on different and diverse topics. So I'm very happy to know that, and you are doing a great job. So good luck with all your master's and PhD projects. So yeah, I moved to IUCA last December, and I joined as an independent fellow. And my goal from my PhD time has been mostly to use optical data and near-infrared data from large surveys like SDSS or DESI, and try to constrain some of the gas properties that is found in and around galaxies, that is known as circumgalactic medium, as well as the gas that we can see in the IGM as well. So I would like to thank to my mentors and collaborators. So these are my PhD supervisors, Guinevere Kaufman and Dylan Nelson, with whom I worked on SDSS. And then I also worked with Simon White for some time to use like DESI and SDSS to do some galaxy analysis. And Joan Tan, she's a PhD student, and I have been mentoring her to kind of like work on absorber properties in TNG 100 simulation. And I also worked with one of my colleagues in Russia, who is an expert in X-ray binaries, and we were looking into like some eROSITA data followed up with DESI and other optical telescopes. And Julian Gee was my postdoc host at Lawrence Berkeley Lab, and with whom I worked on DESI pipeline and developing like the redshift fitter for DESI, along with Stephen Belly and David Schlegel. And I also started collaborating with Brianna. She was a postdoc at that time. Now she has moved to Cambridge. So working on like galaxy correlation. And now I moved to IUCA, where Swagat Mujahid is my postdoc host, and I'm looking into low redshift galaxy evolution using HST and MUSE. So this is just very brief outline of my work. So I'll just start with like a little bit of introduction and motivation, like why do we study metals in circumgalactic medium or intracluster medium or circumcluster medium or IGM. And then I will like show some recent results that I worked on from large surveys, and then what is the next exciting things that we can do along this line, and what are the key takeaways and long-term goals that we can look into, and how we can play a role as a community in India. So let's start with like some of the very known big problems in galaxy formation and evolution. So there are like three big problems that people usually uh, kind of like try to bring forward to the community. One is this galaxy bimodality. So it's kind of, if you see this plot, so if you see this plot here, so this is a specific star formation rate as a function of stellar mass. Specific star formation rate is just the ratio of star formation rate to the stellar mass. And if you can see here, at a given stellar mass, you can easily see that there are two distinct populations of galaxies. One is like blue galaxies and red galaxies. So at a given stellar mass, you see that some galaxies are forming a lot more stars than some other galaxies. So star forming, and these galaxies are kind of classified as star forming and passive. So there has been like a problem of this, why some galaxies are forming more stars and why some galaxies are quenched, means they are not forming stars at all and they're more passive. So this has been a big problem, and people have been kind of like trying to resolve these issues using different observational probes, as well as in the simulation, coming with like, okay, how the star formation rate and the stellar feedback actually kicks some of the gas that is already in the galaxy, or IGM is playing a role. All kind of theoretical as well as observational techniques people have been using to answer this question. Then there is another question that is called missing baryon problem. Though there have been several advances in last few years where people have been trying to resolve this problem. So if you see here, this is the baryonic fraction as a stellar mass. So if you see here, if you combine all the baryons that we can find into stars or interstellar medium, they can only account for 30% of the baryons that we expect to be found in galaxy. So where are the other baryons? So this has been a big problem. And people have been actually trying to observe that, can we see a little far away from the galaxy? Maybe they are there somewhere very far away from galaxy, which is very difficult to see. So that's where this missing baryon problem comes up. And then in similar line, there is missing metal problem. So basically, we all know that like, okay, metals are formed inside the stars, and then stars evolve over the time. And then if the supernova happens, and then some of those metals are kicked out in the galactic environment. So that has, if you see here, this is the component from stars or interstellar medium or all the gas that is found. This can only account for 40% of the metals. So there again, we see that there is a huge amount of metals that we do not see, especially if you see at the low end of the stellar masses. At high end stellar masses, you see that most of the metals, so even if they're like missing, but like all the components have like similar amount of metals like star or ISM. So this has also been a big problem, that where are these missing metal and why galaxies lack their fair share of metal. So these are like three questions that people have been.
So what are these? These are some mass scales you are showing, or?
Yeah, so this one is just the L star galaxies. So this is like typical masses that we say. And then this is from a review paper by Tumunchen et al., which talks about these big problems. So let's say, so can circumgalactic medium be the key? So this is just a very ad hoc, like a simulation, kind of a toy picture of what is circumgalactic medium. So you see there is a galaxy in the center, and then you see lots of things going around the galaxy. There is inflowing material, that is gas, that is being accreted from the pristine intergalactic medium. Then there is a gas that is being kicked out via outflows, either through AGMs or stellar activity. And then lots of gas that has been kicked out, they are kind of like recycling back. They're mixing up and they're again falling back on the galactic disk. So if you see, and this is all happening, so this is like the 15 kpc scale, and if you see, this is like 300 kpc scale. So everything that is in and around galaxies is known as like the within some like a small, we call it like the virial radius. That's how we define given different galaxy size, that number could be slightly different. So here just example like 300 kpc size, and then you see lots of physical processes are ongoing. So the thing is like, so if you see this interplay between all these different processes like accretion, recycling, as well as outflow, is what that actually drives the galaxies and build the galaxies and set their evolution. So basically, CGM becomes a key to understand what is going around and what kind of processes are actually impacting the galaxy formation and its evolution. And theory, simulations, and observations, they can complement each other, though it's difficult sometimes because you may not have a direct comparison with observation and simulations. You have to keep kind of working on improving things, and then keep getting new data and keep getting trying to come up with new methods to compare this data and then see how can we improve our own understanding of the galaxy formation and evolution. So all the problems that I talked about, so like the missing metal or missing baryons, there may be all these missing metals and baryons somewhere here. It's just that we have not seen them yet. So we have to expand our observation from the small galaxy disks, like, okay, where we see the stellar light. We have to go a little far away from that, and then let's see, can we see all those missing? Because this has been a prediction that all the missing metals and baryons that we see are probably somewhere around the galaxies, but this is so diffuse, it's very hard to see them. But now with all the observational techniques, this is becoming possible that we can see some of those missing metals. And that has been the several, last 10 years, there has been several claims showing that they are seeing some of those missing metals and baryons. And similar thing, because this is accretion, outflows, all these processes are happening. That's how we see that there are like distinct population of galaxies at a given stellar mass. So possibly the combination of these physical processes is actually what that gives rise to that kind of a distinct population. So that's also the key to understand the distinct galaxy formation. Viral radius, yeah. So dark matter halo, yes. So I will just focus on this circumgalactic medium basically. So now I'm not going to focus on what's happening at the stellar disk. That is more like ISM studies. So I'll go a little like away from the stellar disk and more towards like a central circumgalactic medium that is like the halo that surrounds the galaxy. So how do we study them? So one of the most important and most studied method is basically to look to detect this gas in absorption against a bright background source, such as a quasar. So you have a quasar, very bright quasar at a very far distance from us, and then light coming from the quasar, when it passes through a circumgalactic medium in foreground or the intergalactic medium, this can get absorbed. And that you will see as an absorption profile on the top of quasar continuum. And then you can study the properties of those absorption feature, and then you can comment on like what kind of material is present between us and quasars. So this has been a technique since last 20, 30 years. And then now with these new surveys like SDSS and DESI, which are providing like millions of spectrum. So where you can actually use the power of statistical analysis. So many times it's because this gas is very diffuse, the density is so low, it's very difficult to see them in individual spectrum sometimes, unless you have a very high exposure time and you can okay, pointing to a particular, let's say, galaxy, and then you want to see with a very high exposure time, you might see a good signal to noise, enough signal to noise where you can detect individual systems. But this stacking analysis allows you to stack millions of spectra and increase the signal to noise, where you can actually detect some of the absorption feature which you may not be able to see in individual spectrum just because of the SNR limitation. So that is becoming a big thing with the large surveys, because that's where you get a lot of data. Then, of course, you can also look this gas into emission, so directly into emission. And that is like emission is difficult because emission depends on your density. So if you have low density, then you know that, okay, emissivity is low. And then if it is very far, then you know it's also very difficult because your flux goes down with distance. However, with surveys like MUSE or JWST and as well as HST, people have been looking into individual systems and kind of trying to see how this halo, galactic halo, circumgalactic medium looks in emission. This is just one example where people have been looking at. So this is like O2, this is like a H alpha emission. So you can look into like, okay, Lyman alpha emission or H alpha emission from galactic halo. And then you can actually see how the fluxes are changing as a function of distance from the galaxy and so on. So this is also very key to, sorry? These are the papers, yes. Yes. Yeah, et al. Yeah. So this is just et al. 2010. Yeah, sorry. Just to save some space.
So you are saying that this is where is this galaxy?
So this is like a so this is like at redshift, I think 3.5 or something, where they're actually detecting Lyman alpha. Lyman alpha emission from that. Yes, yes. So now with this Muse, actually there's Muse Q-based program where they're actually these are like quasar halos basically. So you are actually targeting quasar halo and you're trying to resolve the region around it. So these are like Muse IFU kind of analysis. And then with JWST, now it's becoming even more kind of common, even at high redshifts. That's where people are looking at like even O2 emission, H alpha emission kind of thing. But it's just that like emission is hard. So you may have like just a few handful of samples where you can actually do this analysis. So still this absorption is one of the most important way to do this galaxy observer analysis. And then of course, in simulation where people have basically like TNG simulation, as well as like some recent simulation as like Giebel or FIRE, where people can actually zoom in, means like they can take one galaxy and they can actually go and look into all the physical processes that's happening in our galaxies and how it drives the galaxy formation and its evolution. So that is already becoming very, very important. And now they can also predict like, okay, or how the emission of Lyman alpha looks like around a given galaxy, or let's say H alpha. And then with observation, you can go and actually compare that, okay, does the simulation reproduce some of those things easily, or there is some issues, and then you can kind of feed into each other. So simulation can provide you observables, you can go and look into observables, and then you can provide complementary feedback to simulation that, oh, this is something that you should look into because we are overproducing something or underproducing something. So that's where this complementary analysis of observation and simulation come into picture. And that's becoming a kind of a it's kind of a driving force in the community where people are working together to understand these processes. So, okay. So yeah, so what is my focus? So I will divide my work into two ways. So one is I use these absorption lines, basically that I showed the first method, detected in large surveys and trying to understand the cosmic baryon cycle that connects galaxies, circumgalactic medium and intergalactic medium. And then other is like I also work on data science method for large surveys. So I'll also present some of the work that I did around that direction. So let's start with quasar absorption lines. So as I showed as I showed that you see the absorption line in the quasar spectrum. So you can see like different lines, like, okay, some lines is like magnesium 2, which is singly ionized line. Then you have carbon 4, you have oxygen 6. So basically you can go and find out that what is this line, and then you can compare with your laboratory wavelength, and that will tell you what is this line exactly. And then depending on those lines, because each line will have like different ionization state, different ionization potential, different wavelength, you can actually comment on like what kind of gas this line is tracing. So for example, here I'm just showing a phase diagram, basically the temperature versus number density of neutral hydrogen. And as you can see, if you move up here in temperature, you see lots of ions in very highly ionized state, like neon 10 or oxygen 8 or magnesium 10, all kind of lines that you see. So these are really highly ionized. So they are tracing very high temperature gas and low density. So if you see here, density goes down in this direction, temperature goes up in this direction. And depending on their wavelength transition, you can see at different redshift in different with different telescopes. So like if you have very low wavelength, then if you want to see at low redshift, you have to go in X-ray or UV. But the same line can go to optical if it's very far, right? So
These are for different metals.
yes,
really.
yes.
And this looks like these are measured things.
Yeah, so these are just a simulated CGM from TNG. Okay, so this is like the predictions. Yes, exactly. So this is just prediction just to showing that which lines can trace which phases of the CGM. And it also says that, okay, if we see the CGM, it's very multi-phase. You can see gases up to 10 to the 6.5 Kelvin from 10 to the 4 Kelvin gas as well as. So it's a mixture of all kinds of temperatures. So it's not just one single temperature. It is a mixture of different kind of gas, and depending on, and you can use your own tracer if you want to detect like a particular phase of the CGM. And then depending on the wavelength, you can see it either from ground or space. And that has been one of the driving force using Hubble Space Telescope or SDSS or DESI. So I will focus here, like in my work, I have been focusing on magnesium-2, which is a doublet with wavelength 2796 and 2800. It's a resonant line, and it traces 10 to the 4 Kelvin gas. So we call it like cool in the context of CGM. And
Going back to the previous one where you were looking at, I mean, you don't have to go back. I mean, the H alpha, for example, but that gas is older than this, or
so similar, like 10 to the
similar?
yeah, similar. Yeah, so that's the thing. So these are like, so here is mostly Lyman alpha and H alpha line are showing the cool gas, 10 to the 4 Kelvin gas. So this is like a cool ionized gas we call in the context of CGM. But you also have, like, if you go and look for Lyman alpha lines, then our sodium lines or calcium 2 lines, that is where people are also coming with like what is the neutral gas that you see, as well as like slightly ionized gas and then highly ionized gas, depending on the number density and the temperature. We can define like, okay, it is a cool neutral gas or cool ionized gas or hot ionized gas. That is how like people are just different phases based on the number densities and the temperature. So yeah, some of the hydrogen is ionized, but there's still some neutral gas available. And some of the ionized is mostly traced by these ionized metal lines, low ionization metal lines. But Lyman alpha traces also similar phase of the line, slightly lower than 10 to the 4 or so. So yeah, so as I said, so and then as I'll show, so if you see the absorption line, and if you measure the properties of absorption line, so how wide is absorption line, okay, and how deep is the absorption line, you can comment on like, okay, what is the typical kinematics or like a little bit of number density or how many atoms you can find along a given line of sight. So that helps a lot. And it comes because now you have lots of spectra where you can actually look into this kind of system. So that helps you understand like what is the phase of the circumgalactic medium. And then now, depending on these lines, you can go from like low redshift to high redshift, and then you can try to constrain some of these gas properties from low to high redshift, because you can detect this line either from ground or optical, ground or space at a given redshift range.
Stagnant.
Mm-hmm.
This is for what redshift?
So this is redshift 0. Yes, this is redshift 0. So now go on like what I have worked on. So I started in my PhD, the first project that I did was basically looking into this cool circumgalactic medium. Cool means cool ionized gas, which is traced by magnesium-2 in SDSS galaxies at redshift 1 or so. So at redshift less than 1, basically. So like, so here like I'm showing, so as I showed, so you can have like a quasar absorption line. So you know that there is a foreground galaxy, and then you can, and you have a background galaxy. So you can just see like, okay, how far is my quasar line of sight from the galaxy? So you need like a redshift of your foreground galaxy, and then you can see like, okay, how far in the projected space on the sky this quasar line of sight. So it could like go from, let's say, 10 kpc or like 100 kpc or 1 megaparsec. So basically you try to map this absorption properties as a function of distance from the galaxy. And this is quite possible with SDSS because SDSS gives you lots of spectra, and it's a spectroscopic service. It also gives you redshift. So it's a very precise redshift. So you can measure like distances and angular distances between objects in the sky. So here I'm just showing. So now you have like different types of galaxies. So here I'm something called emission line galaxies in SDSS, which is star forming galaxies. So you see lots of emission lines in their spectrum that is mostly coming from the stellar activity. And then you have red galaxies, which is known as luminous red galaxies in SDSS, which are very bright galaxies, but passive. They're not forming stars. So you don't see any emission lines, but you see there's something called 4,000 angstrom break that you see in the spectrum. And that's how you actually get the redshifts of the, so you can actually fit those lines. And this is how you know that due to the expansion of the universe, the line location changes, and then you can measure the redshift of the systems. So now I have two separate populations. So I know one is forming stars, another is not forming stars. And what I'm plotting here, this is called covering fraction. So basically, it's a number of sightlines with absorbers divided by total number of quasar sightlines. So let's say you have a 10 kpc from galaxy, you have 100 quasar sightlines. Out of 100, only 60 quasar sightlines have magnesium 2 absorbers. So that number will give you 0.6. So that is like the probability of finding a system is 0.6 at 10 kpc. So this is what I'm plotting on the y-axis. That's like a probability. So that goes up to 1 and starts from 0. And then this is a function of distance. So as you can see here, and this I'm plotting for both kind of galaxy because these are two separate systems. So I can plot this plot for both population. And what you see here, below 50 kpc or so, you see that blue galaxies have higher probability to show magnesium 2 absorption around them compared to red galaxies. And similarly, if you go at very large distances, you see that the numbers are very similar. So they are close to each other. And this dashed line is basically that, oh, you do that, okay, I just want to measure this probability around random sightlines. So I don't know that I know that there is no absorption around that line of sight. And this is the number that you see. So as you can see, this is just to show that this covering fraction that you see corresponding to the random sightline is significant enough to say that you still see some detection. So, and then what you can do, so now I know that, okay, within 50 kpc or so, I see some high chances of getting magnesium 2 around blue galaxies compared to red galaxies. Now I want to see that, okay, is it possible that like this is also connected with some of the stellar activity of the galaxies or other properties? So this is where I am showing the same covering factor as a function of star formation rate. So as you can see here, you see a strong increase that high star formation galaxies are showing high covering fraction. It means that around a galaxy which is forming more stars, you have much higher chances of seeing magnesium 2. It means magnesium 2 is tracing cool CGM. So you're seeing that there are a lot of cool gas around a galaxy which is forming more stars compared to a passive galaxy which is not forming stars at all. So, and there you see that your covering fraction is low. Now this is the gas kinematics. So basically you are just saying that, okay, how fast is gas moving around a given galaxy as a function of halo mass. And what we see here, this is blue is for blue galaxy, red is for red galaxies. As you can see, at any given stellar mass, any given halo mass, you see that gas is moving faster than around blue galaxies compared to red galaxies. So there is means that gas is more and more kinematically kind of active around blue galaxies compared to red galaxies. So this has been so if you see, so cool gas, and since we know that in star forming galaxies you are forming lots of stars, so you need a lot of fuel. Every time you are forming stars, you need a lot of fuel to form the new star, generation of stars. So and as you can see, this covering fraction, which is the probability of finding an absorber, is also higher around the blue galaxy compared to red galaxies. And also the gas kinematics is also different. So one thing that we could comment on, that this cool gas around star forming galaxies have different origin than quenched galaxies. So one thing is like how they are different. So in star forming galaxies, you are forming lots of stars. then stars are evolving, they are dying, and then some of those metals are kicked out from the galaxies. So you can like, okay, and then there are like models that can actually help you understand, okay, you have a stellar supernova, and then let's say you start with some very high velocity of the gas that has been kicking out the material, and then you can measure in some toy model that, okay, what will be the expected velocity of my kicked out material at a given distance. So that number comes around this 100 kilometers or 200 kilometers that I showed in this plot. This 100 kilometer, that comes around similar number for star forming galaxies. And so that helps you understand that, okay, the stellar outflow is one of the key contributor. Yes.
The
Yes.
width of the magnesium line.
Yes.
The width of the magnesium.
So, and then, but in the passive galaxies where you don't see any stellar activity, but there is a lot of accretion that is going around. So there is a lot of gas that is formed, that is actually being accreted. And the thing is that, okay, ideally that all the gas that is being accreted, if it falls on your stellar disk and you get like, and it falls into a stellar disk, and it cools down such that it goes into molecular hydrogen-less state, then you can start forming stars. But this is not what's happening around these LRGs. We see that there is accretion of gas from previous literature. However, this galaxy is passive, means the gas is either not reaching to the galactic disk or it's reaching but it's already heated up, means it's not cool enough to actually go and create like the molecular hydrogen that will form stars. So that is another thing that but however you see lots of cool ionized gas, is just that it doesn't end up forming stars. So that's where like in the simulation people say that one reason is that very massive galaxies, they also contain AGNs in their center, and AGN is one of the key contributor that it doesn't allow gas to cool down, or the gas is following but it also kicking out the gas out of the galaxies. So that is one reason that you do not end up forming stars in this galaxy. This is one of the mechanism that people come up with saying, and this is what you see, that you still see a lot of cool. So initially people thought that around passive galaxies there are no cold gas, so that's why you don't see a star formation. However, this analysis show that you have lots of cool gas that could have ended up forming stars, but they're not forming stars. So there is other mechanism that is not, and that is preventing this gas to cool down and form stars. So that is one thing that in simulation people have come up with. It's massive galaxies, possibly because of the AGN activity, because you see a lot more AGNs in massive halos compared to less massive halos.
If you think that these gas are due to stellar outflow or accretion, then that won't be random velocity, but velocity. So but the magnesium line you are seeing at the redshift of you don't see any redshift or redshift there.
Yeah, so that's the thing. So you can actually, if you know the systemic redshift of the galaxy, this is what people also do. I will show just one method that how people do that. So what you can do, you can say that, okay, I know the systemic redshift, and then how far I am from that redshift, either negative or positive, and then I can comment on like, is it like outflowing gas or inflowing gas? As well as if you know the orientation of galaxy, then if your sight line is crossing either through major or minor axis, that can also help understand if this is gas is more kind of like towards major axis or minor axis. And that's where people try to come up with that in the star forming galaxies. They see that most of the magnesium is around the minor axis, where you have outflows have higher chances of escaping compared to the major axis. However, in the accretion, they see that gas is more towards major axis. So that is one aspect that people have been trying to come up with, that this from the magnesium 2 and the line of sight orientation, you can actually comment on, is it like outflowing gas or inflowing gas. However, in our analysis, it is difficult to say because this is not like galaxy is like quasar line of sight. So it's very difficult to say that, and this is like statistical samples. Yeah. Yeah, so and this is what like I will show where we are actually have written a proposal for HST to do that. So this is more like, okay, but here you see that there is some strong correlation between star formation rate and the chances of finding magnesium. So that kind of like gives you a direction that, okay, star formation is a key contributor to some of these properties. However, in the passive galaxies, you don't see, but you see a relation in halo masses. So you see, like I did not see here, but what we also find, if you have a very massive halo, then you have a very low covering fraction. So that also, and that is like due to two reasons. One is like high massive halos have higher virial temperature. So you have like yeah, the gas is mostly very high at temperature. So yeah, exactly. So that's why you don't see. So that is another reason. And other thing is like, okay, you see, and because as you said that it's highly ionized, so you don't see in magnesium too. And that's why people have been looking into highly ionized as a function of halo masses as well. So now I moved, now I extended my study to galaxy clusters. We all know that galaxy clusters have been observed mostly in X-ray, and the intracluster medium, that is the gas in the cluster, is mostly very, very hot. And it's like 10 to the 7 Kelvin, and it's mostly detected in X-ray. So that is one thing that we already know about the clusters. However, when we actually looked into magnesium 2, so now we have also galaxy cluster catalogs from SDSS as well as DESI, and the same quasars that we can use. So now rather than a foreground galaxy, we can say that, okay, this line of sight is passing through a galaxy cluster. And there what we found that even though galaxy clusters are very hot, intracluster medium is very hot, we still see that clusters have higher magnesium to surface mass density, which is the mass divided by the area, basically angular area. So we see lots of cool gas, even though the cluster is very, very hot. Intracluster medium is very hot. So it means that intracluster medium is also very multi-phase. It means there is a gas up to 10 to the 4 Kelvin gas, and then in X-ray, people can detect up to 10 to the 6, 10 to the 7 Kelvin gas. So there is a diversity of phase in the intracluster medium and then there was like also, and if you see there like something called cool core clusters, where people see lots of cool gas near the center of the cluster. But the intracluster medium is more diffuse, and you see a lot of hot gases all around the cluster.
So,
yeah.
These are all like average. I mean,
yeah.
How many clusters roughly you are using? Let's say the DESI clusters.
So yeah, so DESI is around 70,000 clusters.
Another thing is that for the ELGs, the emission line galaxies. So these are what the clusters were identified with emission line galaxies.
Yeah, so clusters identified in optical basically. So with some group algorithms, yes. So it's optically identified, but we only took those clusters where we knew that the brightest cluster galaxy has a spectroscopic redshift. And then from the imaging survey, what we did that, okay, for a given brightest cluster galaxy, we used the photometric redshift, but we tried to find how many galaxies that you can find around that bright cluster galaxy, let's say within 1 megaparsec or so. And then what we also did that, okay, we know that, okay, our line of sight is some 100 kpc from a brightest cluster galaxy. Then we also looked for, is there any cluster member close to that galaxy? So maybe this line of sight is actually part of CGM of those cluster galaxies. And in that way, we try to see that, okay, is it also connected with any of those cluster galaxy properties? But we did not find any physical correlation. And that is why what we concluded that what gas that we are seeing here is mostly in the intracluster medium. It's not part of the circumgalactic medium of those individual galaxies that are part of cluster galaxies. And it is in intracluster medium. So
it seems that the SDSS ELGs, they are consistently higher.
Yes.
Up to 20 R500. They are consistently higher than the other ones.
Yes. So one thing, yeah, so this at smaller distances, as we saw that covering fraction is also higher in and around ELGs in the previous study. So that is also contributing to the fact that you are getting more and more magnesium 2 absorption because you have higher chances of detecting magnesium 2. However, and these are like, if you see after like, this is divided by R500. Yes. So, and then around after 2 R500 or so, you see that starts, and then as you said, like a 20 R500. So here also one thing is like some of this ELGs is still part of some of the cluster galaxies. That is also possible. And other thing is that we in the, as you can see here, yes, yeah. So even here, like it's like 1 megaparsec or so, you are seeing that it's now converging to the random value. So 1 megaparsec is corresponding to very high virial radius for this 10 to the 11.5 solar mass Hale mass. Yeah. Yes. So you see that, okay, these are like converging at very large distances. Mostly this is where this IGM contribution starts taking over. And this has been also, if some of the previous studies have also shown that some of the LRG which are part of dense group, you see the contribution from the nearest neighbors, basically. So you have like one central galaxy, but then you at, let's say, 1 arc virial or so, you have like another satellite galaxies that also contributes to your gas profile. And people have used these 2 halo models to model some of these gas properties. And this is how they fit this LRG especially very well with this. And with similar method, we could also fit with this cluster galaxies where you see some contribution coming from the galaxies. However, as I said, they were not correlated with any of the cluster galaxy properties. So it may have been originated from the circumgalactic medium of the cluster galaxies. However, given the times, because these are at 0.5 redshift clusters, that they, yeah, exactly. So they have got enough time to go out from the CGM of the galaxy, but not enough time to get heated. Yeah. So that's also one of the. And this is the work that I presented in ASI, which here I am looking into carbon-4 systems. So as I said, magnesium-2 is a tracer of 10 to the 4 Kelvin. This is even higher state, and it tracer 10 to the 5 Kelvin gas, which is like warmer phase of the CGM. And so here I'm not doing any cross correlation with galaxies. Rather, I'm just taking the absorbers that have been found in DESI quasars and then using that absorber to kind of constrain the omega, which is the matter density of carbon-4, because carbon is third most abundant element in the universe. So that helps you understand that how is the metal changing over the universe evolution. So as you can see here, this starts from redshift 5.5 or so. This is like some previous analysis, and this blue is basically the analysis from our DAISY paper. And these are like some also some SDSS analysis. So as you can see here, we see from redshift 4 to up to 1.6 or so, you see more and more carbon being produced in universe. And that is kind of like expected, because as the universe has grown, more and more galaxies have formed, more and more stars have formed, and that has helped contributed kind of increasing the amount of carbon being produced. However, you just don't need carbon, right? You first need carbon, then you also need like the mechanism and also the situation in which that carbon is converted to carbon-4. So you need like neutral carbon. Either it has to be ionized by photoionization, means you have massive stars that can generate UV photons, or you need some AGNs that can actually heat up. And also because these are intergalactic medium, these are not close to galaxies that we don't know. So means you also need to throw them out in the universe. So that's where this AGN as well as stellar feedback both are coming into picture. And this is the metallicity. So you can use the carbon-4 column omegas, like matter density, and you can use relation like, okay, what is the expected carbon that we see in universe, and how much of that carbon is in triply ionized carbon form. And you can use to actually get some constraint. These are like lower limit constraints on metallicities in the universe. So this is metallicity, means okay, how much metal you see in the universe at a given redshift. So as you can see, as the universe has grown, you see more and more metals, because as you can see, carbon is kind of a very good tracer of metals in the universe. So that trains becomes very visible even in the metallicity, because it's one of the traces. So clearly you see more and more metals as the universe has evolved. And as the universe has evolved, more and more stars have formed, more galaxies have formed. So the mechanism by which you heat gas, that has also evolved with time. So basically you produce your ultraviolet radiation that can heat up either by ionizing, by photoionization, or you can have like collision among each other, and that can also heat up some of those carbon to carbon-4. So basically that gives you an idea like how the metals have evolved as a function of distance, as a function of redshift in the universe. So these are DESI quasar, just looking into quasars spectrum. So these are just, this is a blind survey. So there is no galaxy close to this C4 observers, as we know. But you can now, you can look for a galaxy, let's say, and then you see that how many carbon 4 that you have detected. No, so these are like outside lemon alpha 4s that I'm looking into. Yes. Yeah, because in lemon alpha 4 it's difficult to see that which is actually carbon 4 and which is actually lemon alpha. So these are outside lemon alpha forest. Yes.
They're all DESI. So slow or DESI quasars.
These are DESI quasars.
These are DESI quasars. But when we're talking about the omega,
Mhm.
I mean, how complete is this prediction? And you are just, is this sample very well sampling of what you call omega C4, right?
Yes, yeah. So this is like a 3,000 quasars, 300,000 quasars from DESI between redshift 1.4 and 4.5. So then, and this is also, we have also applied the completeness correction. So yes, yes. So this is, I did the completeness correction. So these are, but still because this omega depends on the column densities, and in low resolution spectrum, you cannot get like the very accurate measure on column densities. So these are like kind of, you can say that these are like a lower limit on column density. So that can give you that, okay, your omega is very tightly constrained in the lower limit range. So that's why you see some of these are coming from some high resolution spectra, and you see that the numbers are a little higher. But this is like, we know that it cannot go below than that. And similar in metallicity. And that's where people have been seeing that, okay, in CGM or in the galaxy disk, the metallicity is like close to solar metallicity or 10 to the minus 1, but in IGM is 10 to the minus 4, 10 to the minus 3.5 kind of thing. So that clearly shows that IGM is, of course, not as metal rich as galaxies, but you see some good trend of metallicity in the IGM. So yeah, so now this is just like I'm comparing, sorry, I'll just 5-7 minutes to the, okay. So now this is, as I mentioned, one of PhD student I have been working with. What she is doing, so she is actually using TNG simulation and kind of generating the mock spectrum. So there, you know, what is the number density of gas particles of all kind of like, let's say metals. And what she is doing, she is actually generating the spectrum with similar resolution as a given instrument, let's say DESI or STSS. So this is, she has generated DESI spectra from TNG 100. And what we did, we also used the same method to measure the omegas in the, sorry.
How are you doing the spectra from TNG? I mean,
Yes, so she is using this PyGAD basically, which is like, okay, you have a box, then you just shoot a random sightline in the box. And now you know that, okay, what is my column density of carbon? They know that, like, what is the fraction of carbon is in carbon 4, what are the column density along a given line of sight. So you can actually measure your equivalent width.
then you construct.
Yeah, exactly. And then you convolve with, yeah, exactly. Yeah, exactly, to get the same resolution. So what we are finding, so this is this intrinsic. So you just count everything in your simulation. So that gives you intrinsic omega C4. Means you get all kind of systems like very strong absorbers, very weak absorbers. In observation, what happens, since you are limited by your signal to noise of your spectrum, you can only go up to a particular limit. So you cannot go and find like very, very weak systems, because your observation may not allow to find them because it's just lost in the noise. But in simulation, you know, because you have run your simulations, you know, like, okay, how many particles do I have? How many particles are in carbon 4? How many particles? Because you have some physical mechanism to generate them. So this is, if you see, the intrinsic is much higher. So, and even if I apply some cut on column densities, I still see that omega C4 is being underproduced, if you see, compared to observations at low redshift. Sorry, overproduced at low redshift and underproduced at high redshift. So TNG is not doing very good in global statistics, even though they produce amazing results for, let's say, galactic properties, but the global properties, they are failing. So that's where it is kind of a feedback to the analysis TNG group, that how you can improve these things, because these are like, there are a lot of free parameters. You have to tune some of these things and then you ruin some other things. So this is what, like, global properties, they're not doing very well. So this is one of the results that we are writing up. And then what?
Is because we are producing data in a different way,
Yes.
or they are distributing the
Yeah,
data
so I think it's both. Both, yeah. So in distribution, definitely because they have these AGN mechanisms, so they turn off or turn on. Exactly, exactly, exactly. Different AGN modes. Yes, yes, yeah, exactly. So it's all, yeah, IMF, yeah, exactly. And even if you see their metallicity, total metallicity is also very like either they're producing more metals at a given redshift or underproducing. So as you said, it's a combination of both production plus distribution. So that is both the scenario, and that's where now they are coming up with like new feedback models where they want to, okay, at a given redshift, I want to reproduce. So what are the best thing that we can do there? So anyway, this is one of the feedback that that is already, and this is not just TNG, it's most of the simulations because there is always different mechanisms by which you produce metal and by which you distribute metals. So now what I am also doing is that like not just the magnesium 2 or carbon 4. So because I have a method to kind of detect all kind of systems, basically doublets, because it's easier to detect doublets because you have other line to confirm. So, and using DESI spectra, so I have now lots of different ions. And now I'm working on how to constrain this omega ions, basically. So that will give an idea on like how the omega of different phases of the gas is evolving over the universe time. So like, for example, nitrogen 5, silicon 4, and they all trace like slightly different phases in the CGM or the IGM. And since they can be detected at different redshift, you can always use like your galaxy catalogs to kind of connect. I was showing this cross correlate with your foreground galaxies, or let's say you have foreground AGNs or you have foreground quasars, whatever foreground object, and then you can just study these properties. So that will help you understand that, okay, what is happening to cool gas, slightly warmer phase of the gas, or even the hotter phase of the gas. This is what people do also in the X-ray as well as in UV. So this is work in progress. So, and then I moved on to now I was showing this magnesium 2 as a function of distance, but now DESI also allows you to go into little more, and you can go and look for both magnesium 2 and carbon 4. So not just one line, but you can also look for both lines. There is a nice redshift range from 1.4 to 1.7 where you have enough galaxy to do this analysis. So as I was showing, so this is your quasar. This is your galaxy pair. So it's like, and let's say, for example, you have 60 kpc, and now you can look for these both systems. So this is just one example. So this I have just stacked the spectrum as a function of distance. So I find, let's say, 100 spectrum within 10 kpc, let's say from galaxy, and then I can just stack those quasar spectrum. And this is what you see here. You see lots of, so these are the lines that you will not see in individual spectrum because individual spectrum does not have enough signal to noise, but now you see a lot more lines. So you see magnesium 2, iron, whatever line that you can cover in your wavelength range, you can see most of those lines. And now you can actually measure these properties. You can measure the width of the line, you can measure the equivalent width of the line, you can measure like the how much is the strength of the lines, all those things. And these are like as a function of distance from the galaxy. So you can actually, this is, I'm just showing here, this is, I'm just measuring the equivalent width, which is just gives you like how much power has been lost due to the absorption. And this is as a function of distance. So as you can see, and this is very preliminary, so we are still kind of have started this part. So as you can see here, at very small distances, 20, 30 kpc, you see that magnesium 2 absorption is higher compared to carbon 4. Means you see cool gas is more, you find more cool gas near the galaxy. However, as you go far from the galaxy, you see that you see less cool gas compared to your hot gas, which is traced by carbon 4. And also, if you see the decrement, if you see the slope, you see that cool gas equivalent with declines much faster compared to a warm gas. So that is also kind of, as I was showing initially, that most of the gas that you see in the CGM is in the hot form. And it's difficult. That is why it becomes difficult to see them, because these are very diffuse. and emission is actually proportional to your number densities. So it's very hard to see them unless you have very dense phase. It's difficult to see them. And here you see also that carbon 4 is more diffuse compared to magnesium 2. And this is just like preliminary. But now, since we have good sample, actually we can do the seam stacking analysis as a function of distance, as a function of stellar properties like stellar mass or star formation rate of these galaxies. And that will give us like an understanding, because this is at redshift 1.4 to 1.7. That is also crucial redshift because it's close to cosmic noon. So you know that at this redshift, you see lots of star formation happening. So that will help understand actually how this cool and warm gas are interacting around galaxies. So, and this is another example. Okay, sure. So this is another example that we are looking into. This is like how does AGN feedback impact the CGM? So as you were asking, so this is one of the proposal that we have recently submitted, but we don't know if it's going to go through. So let's hope for a positive news. So what we are looking into it. So what we did, we took all the DAISY AGN sample, and then we cross-correlated with the HST quasars. So lots of HST, basically cosmic origin spectrograph, has observed lots of quasar spectra. And this is from the previous analysis where people could go up to redshift 0.1 or so. And now we are moving it to redshift 0.1 to 0.2, so like slightly higher redshift. And our goal is to look for O6 line, which is 1038 angstrom. So where you can actually see in cos spectrum, because this is UV from space. And this also shifts to the redshift, higher redshifts. Our goal is, if you see, these galaxies are above 10 to the 0.5 or so stellar mass. And these are AGN. So these are basically slightly massive AGNs, where you can actually look into what is happening in the halo of the AGN. Basically how this gas property is varying as a function of AGN. And that will help us understand that, okay, if it is different from the normal galaxies. And because for normal galaxies, there are a lot of studies, but for AGNs, because we did not have many AGNs detected around this redshift. So this is where this DAISY cross-correlated with HST is coming into picture. And we have asked for 23 orbits, and this group had asked for 55 orbit. DAISY AGNs. It's a BPT diagram. Yes. Yeah, AGN. Exactly. DAISY, and then cross-correlated with HST spectra. Yeah, quasar spectra. So, and because now we have a good sample, so we can actually shift this redshift as well. So we have like lots of samples, like around more than 10 actually. Out of these, so we had around 13. Out of 13, actually, 4 were already observed in HST. And then we have asked for re-observation because the signal to noise is not good enough. And then there we found like new quasars that we can actually observe with HST. So we found like 8 quasars that we can observe. And so we have asked only for 23 orbits. And this group had asked for 55 orbits, and they had got time. So that is one of our arguments, that we are actually pushing this to higher redshift, and we can do it even low number of orbits. So let's see how it works out. So now I'll just move to simply very quickly. So as I said, I'm also very interested in doing data science. So I have developed a few pipelines for big surveys, basically SDSS, DESI, and all the upcoming ones like Foremost and other ones. So this is called NMF QSOFIT. This is a quasar continuum fitter. So as I showed, all analysis where you're looking for absorber, you actually need to have a quasar continuum. You have to model your quasar continuum such that you can remove the quasar continuum from your spectra, and then you can look for absorption features. So this is a machine learning method where you use this non-negative matrix factorization. Basically, you just take your quasar continuum, quasar spectra, and you kind of like generate few basis vectors like principal component analysis, but it is non-negative, means you are not going to include any negative pixels. But if you see now lots of spectra, if you see, there are many negative pixels, but that is all due to because either you did some sky subtraction not very well, or your flux calibration went wrong or something. But you know that in principle, fluxes should be positive. So that is how we use this. And then you can apply to any sort of like a DESI spectra or SDSS spectra. Now we are working into looking into HST spectra as well, such that we can generate quasar continuum for that, as well as foremost, which is just started looking into spectra. So that's this is a kind of a generic fitter that can be used for different surveys. This is just one example I'm showing from DESI, where you see this flux and continuum that we measured from this method, and this is publicly available, so anybody can go and have a look, and if they find it useful, they can use it for their own analysis.
Continuum plus emission.
Yeah, continuum plus emission. Yes. So this basically, because this I train it on all the quasar spectrum from DESI. So DESI has the emission plus continuum, so it gives you both, and then you can do your own if you want to apply some more, like, okay, I want to have more smoothing, or more like I want to use like slightly more number of components because I want to get better fit, or my noise is high. So all those things you can do out of the box from the pipeline. So as of now, no. So when I generated the eigen spectra, the basis vectors, then I tried to generate in different redshift bins, such that I can cover the wavelength pretty well, such that I have enough number of quasar to generate in each redshift bins. So signal to noise we did not apply, but like a very basic signal to noise that, like, we know that this spectra cannot be used from DESI. Let's say exposure time is very low, so we know that, okay, this should not be used. So that kind of cut, but not some very high signal to noise cut kind of thing. So in general, we had around 100,000 quasar spectrum, which we use to train our method, and then you can run it on other quasars. This is another pipeline that I designed to detect these absorption lines. So once you have the continuum, you remove your continuum plus emission from spectrum, and then you run this pipeline to actually find this doublet system. So this is one example that I'm showing. This is magnesium 2 that pipeline finds. So you can, and this is also very generic. So you can define your own doublet, and you can use your, like, okay, I want to search for magnesium 2, carbon 4, or any kind of doublet in the low resolution spectra, and it will find out for you. And then this is the redshift fitter that I worked on when I was part of DESI. I'm still part of DESI, but not like as an active participant, but as a continuing participant. So this is basically, you have several hundreds of thousands of millions of spectrum, and our goal is to get their redshift. So this is like a PCA-based method, principal component analysis method, machine learning-based method. So you generate your components, and then you have a spectrum, and then you have redshift grid. So you basically fit at each redshift grid, and then you minimize your chi-square, basically. So, and that will give you a redshift where the chi-square is minimum, and that is kind of your redshift. And for example, if you see here, so what we did here, and then what we also added, like, okay, apart from PCA, I also add that, okay, we have a synthetic spectrum, which we know this is a synthetic galaxy. You combine your approach with PCA, so that gives you enough speed to run on millions of objects. And that also allows you to get rid of things where PCA fails, especially because PCA is just a machine learning method. It doesn't look for that if flux is negative or positive. It will just try to minimize your chi-square. So if, let's say there is a bad pixel, there is a very bad negative dip, PCA will think, oh, I have to fit this pixel because that's how I can minimize my chi-square. And it will fit a very bad negative absorption feature as a kind of a real feature. So that's where this synthetic spectra helps you out, because synthetic spectra won't have any unphysical features, right? So for example, here, if you see, PCA says that, oh, this is the redshift at 0.84 because it misidentifies this O2 line as O3, because it tries to fit actually a negative dip somewhere. So that's how the line got shifted. But when we ran with this, our PCA plus a synthetic spectra, then we see that, oh, this is actually an O2 line. So the redshift is now, if you see, 1.46. So this is the real redshift for this object, but the PCA only gives you 0.83 redshift. So that's how you can actually improve your redshift fitter. And this is kind of being run with DESI. So we are getting redshift based on this combination of PCA plus your synthetic spectra. That is a little slower than PCA because it has to do another set of tests kind of thing. So these I'm just This I'm just showing an example, but we have like archetypes, this synthetic spectra for galaxies, quasars.
And easily
Yeah, so
identify
yeah, so this is because this emission line galaxies, we have designed the DESI instrument in a way that it can resolve these O2 lines such that you can go up to 1.6 or 1.7 redshift. So for low redshift galaxies, of course, you see more lines, and then that gives you more confidence. But this is more kind of useful at slightly high redshift, where you other lines are far behind your far like away from your wavelength range. So that is how it has been designed, such that you can target even high redshift O2 emitting lines galaxies. And then I'll just mention a little bit about like, so I got DESI Builder Award because I worked on pipeline development, and as well as I was also working on survey operations, like how DESI does the survey on daily basis. And that gives me access to the proprietary data. And I also worked on DESI cosmology data analysis by getting the redshift for the community. I also look for these cataclysmic variables with my colleague, Ilham Galiulin. Basically, he looked into E Rosetta, and they were looking for cataclysmic variables, and we kind of did a follow-up with DESI to kind of do the optical follow-up those cataclysmic variables, as I showed. Metals in TNG 100, I'm working with PhD student. I'm also working with Parayag, who is a PhD student at Central University of Himachal Pradesh, working with ultra strong magnesium 2 absorbers. Then I'm also working with Sumukha Bharadwaj. He's a PhD student at IIST. We are looking into low redshift weak MG2 systems with HST and DESI. And as I said, I'm also now part of Nancy, which is a Nancy Roman community survey. So it's more like a Lyman alpha, more like infrared galaxies at redshift 3 or so as of now. The Nancy will come online maybe next few years. And recently I was also awarded Max Planck India Mobility Grant. So that gives me some money to go and spend some time at Max Planck for next 3 years. And so I'll just quickly go here. Sorry. So what are the future things that we can do? As I said, this 1 to 3 is the cosmic noon, where you see that star forming history picks up. You see more and more stars. And as I showed, this is omega of carbon-4 and other metals as a function of redshift. As you see, as you form more and more stars, you start seeing more and more metals. And this is all happening between redshift 1 to 3, where you see lots of activity going around. And this is, I'm just showing neutral gas, Lyman alpha, up to, let's say this is 06, 07. This is 10 to the 6 Kelvin gas. So you see, these are all found near the galaxies within 100 or 200 kpc. So that easily shows you, as I was saying, that the CGM is very multi-phase. These are all observational results. So you see lots of cool, warm, and very hot gas around the galaxies. So same picture, this is all happening at redshift 0. Our goal is to actually make the same picture at redshift 1 to 3. That's where the power of new surveys like DESI, SDSS, Foremost, as well as JWST comes into the picture. So that's our goal, that we want to create the same picture, but at redshift 1 to 3, where the most of the star formation activity is happening. So as I said, and this is also one of the science goals in ASI's vision document, if you see, that was published in 2024. And that's where, if you recently may have seen the news, that India has announced new big telescopes that will come online in next 20 years, next 15 to 20 years. So that will be like 13-meter telescope with spectroscopic instruments. So that will also be a great thing to do in next couple of. So we have to be prepared with the things that will come online in next 5-7 years kind of thing. And this is how I'm just showing. This is just existing data that we can use to do this kind of analysis as of now. But if you want to go into, let's say, higher metal state, then you have to have more and more galaxies at this redshift, but we don't have as of now. But with time, we will see more and more space on this plot will fill up. So that's how the immediate data that we can actually use either from DESI, PFS, or HeadTex, all this existing surveys. And that's where, like, when the Indian telescope will come out, we'll also fill up some of these gaps here as well. So I'll just move to, yeah, so this is just one thing I wanted to show. So this is, I was talking about CGM in emission. So we can do actually CGM in emission as of now also with survey data. So DESI also observes, apart from galaxies and quasars, it also targets the sky, like blank sky. You just target your telescope in a blank sky location, and you can look at the sky spectrum. Means there is nothing there. You just see the sky emission that is coming from foreground or background. And then you have millions of spectrum like that. You just stack them together, and then you say that, okay, what is my typical sky spectrum look like at a given, let's say, distance from a galaxy. So rather than connecting with a background source, you say that my galaxy is close to this sky spectra. So some contribution from the CGM of that galaxy is actually part of this sky spectrum. And this is one example from SDSS where people actually did this analysis with 0.5 million spectrum. And they found that they can go up to 10 to the minus 20 or per centimeter squared per second per angstrom. So this is the limit that they could find. But now with DESI, we have around 4 million spectrum. So we can go even up to faint emissions. So that's what as of now we are doing. That if we can detect some of the very faintest emission from the CGM of the galaxies. So that will be a good thing to do and understand how CGM is behaving in emission. And as you were talking, this is one example where people actually do this stacking in the rest frame of the galaxies. So you stack galaxy in the rest frame of a foreground galaxy, and then from the shift in the line, you can actually comment on if it is like outflowing gas or inflowing gas. The only disadvantage is that like you cannot do it as a function of kind of a distance because you may not have very samples. However, you can comment a lot on like, okay, what is the gas kinematics? So that is one thing that this is from SDSS, but similar things can be done with DESI, and we can see more and more. And this is synergy with simulation, as I showed one example. And this is another example where people are looking into different observables in simulation and trying to match if it matches with observations or not. So as you can see here, the gray points are observations, and the dash and solid lines are simulations. As you can see, simulations are sometimes overproducing or underproducing things at a given distance. So I'll just stop here. And this is my summary. So basically, you want to combine theory, simulations, and observation using different techniques and developing that our goal is basically observer galaxy correlation, emission line, and as well as like simulations, how we can compare simulations and complement each other. And that's the plan, that you need this kind of techniques, either spectroscopy, imaging, as well as simulations, either in situ simulations. That some of the simulation, if you see IUCA is involved, Ninja is one of the simulation that is coming from India now. That is also large cosmological volume hydrodynamic simulation. So that's where like we are actually, that will be a great to kind of combine all of these things together and come up with a coherent picture to characterize the circumgalactic medium and connect it with galaxy formation and evolution. Thank you.
So, questions, okay? First, Observational, yes.
Can you go to the carbon 4